This podcast is on the kinetic molecular theory. It is an affirmation of the gas laws, because you'll remember that theories explain why things happen, and the kinetic molecular theory, which we will be abbreviating KMT throughout the course, explains why the ideal gases behave the way that they do. It's based on a series of postulates, the first of which is that gases consist of tiny discrete molecules that are relatively far apart, and indeed a gas sample is mostly empty space. But it is composed of these molecules which are in continuous random motion, and in this random motion they collide with each other and with the walls of the container. All of these molecular collisions are elastic, meaning that no energy is lost in the collision. And finally, this energy, the average kinetic energy, is proportional to the Kelvin temperature. What that means is that the particles don't affect each other, neither attracting or repelling each other. They're so small we can ignore their volume in calculations, and the pressure is due to the constant collisions of the particles with the walls of the container. Now, appendix number 2 in the Zumdahl textbook shows the derivation of the ideal gas law, the definition of temperature, and much more. And if you're so inclined, you can go for a more rigorous mathematical treatment of what you're about to get here. What you're about to get here is dependent upon you remembering that kinetic energy is 1/2 mv squared, where v squared is the velocity of the object squared. From appendix 2, we know that kinetic energy is 3/2 RT, R being the universal gas constant and T being the temperature in kelvins. This, in fact, is how we define temperature. And we're going to use mu to represent the particle velocity. So mu bar is the average particle velocity, and u squared bar is the average of the squared particle velocity. What we're interested in is what's called the root mean square velocity, which is, in fact, you take that average squared particle velocity and then take the square root of it. Well, for a mole of gas, the kinetic energy is equal to Avogadro's number times 1/2 the mass times the average particle velocity squared. It is also 2/3 RT. Well, we can combine those equations, as we chemists love to do, and you end up with an equation that says the average particle velocity squared is 3RT over Avogadro's number times the mass of the individual particle. Well, that's not totally bad. M is the mass in kilograms for one particle, and N sub A times M is the number of kilograms for a mole of particles, which is the molar mass. So we end up with the root mean square speed equal to 3RT over the molar mass. But you need to remember that the molar mass is in kilograms per mole, not something that's very common. And we have to have R in the proper units for this. R has the units of 8.3145 joules per kmol, because the joules is how we introduce units of meters per second and kilograms, and we're unit consistent. So we get a velocity in meters per second. Let's look at an example. Calculate the root mean square velocity of carbon dioxide at 25. Well, the molar mass of carbon dioxide is 0.04401 kilograms per mole, so you substitute it into the root mean square equation, and you get 411 meters per second. What it would be wise to do is stop the podcast and do the next 2 problems and compare your answers. One is hydrogen, the other is chlorine, and see if those values make any sense to you. The average distance a molecule travels before colliding with another is called the mean free path, and it's very small, like 1/10 millionth of a meter. Inside a gas, we also have something known as the temperature. But that temperature is just an average. Many molecules are at speeds other than the average. And so what we have coming in the next slide is a graph called the velocity distribution. And I'd like you to examine it, stop the podcast, and make some generalizations about what you see. What I hope you saw was that the average velocity of the particles increase as the temperature increases. I hope you also notice that the range of velocities increases as the temperature increases. And in Appendix 4, this particular equation shows up. It is a way of calculating the velocity range, and I would suggest that you have a look at it and know that it will never appear on an AP exam. And we're going to use this velocity idea in our next podcast, which will be on effusion and diffusion.